Progress.
Hi, Jordan. How you doing?
Good. How are you?
I'm doing fine. Did you get your test back?
I think so.
It was, I think, a CB-ish.
Yeah, I think it said like a 106 out of 150.
That is C level, okay?
Yeah.
Jordan, it's a tough course. What can I tell you?
Yeah, I've some questions I thought were hard, and there were some where I was like, yeah, it's okay.
What I tried to do, Jordan, was I tried to give the first couple questions as being plug-in answers. Clearly, I threw you guys by the indicator question and especially by the titration question. I was getting answers all over the board for that. So literally speaking, I thought I was being kind by giving those questions because I thought they were pretty much gimmies.
I know I personally had a hard time with the titration question.
You're muted. I can't hear you, Jordan. Try speaking. I am sorry. Can you hear me? Can you shake your head if you can hear me?
Okay, now I can hear you.
Okay, I don't know what happened there.
It said that my internet connection was unstable.
Better the internet connection than you. Hi, Jessica. How you doing? I don't know how much I'm going to be able to stall here. You guys have had single replacement reactions, right? Do you know what I'm talking when I say single replacement reactions?
Yeah, I think so.
Jessica?
Yeah.
All right. What I think happened was, I think the guy that designed the course was looking for simulations, anything he could grab that would have some sort of a semblance on this. All right. These are going to be normal single replacement reactions. You're going to be asked to stick a metal into a salt solution to see if you get a reaction. Pay very close attention to the temperatures that you're getting there, okay? And depending on circumstances, I may even show you a way to get around it, okay? And that, literally speaking, this lab is really to show you next week's lab or Tuesday's lab, because Tuesday we're doing something called standard potentials. And if you guys are willing, I may just go ahead and do the whole thing today. And on Tuesday, the reason I will give another talk on Tuesday. That's going to be pretty much optional for you, because it just doesn't make sense to do this without doing the other thing. Does that make sense to you guys? Jessica, you good with that? And the bottom line, it means that you're not going to have to show up on Tuesday. I will be here on Tuesday to re-give that lecture, but you won't have to be, okay? Is that fair enough, guys? You guys should be rewarded for something anyway. Okay. All right. Jolene's is joining us in a second, and I guess my J girls are all showing up then. Jolene, don't yawn. She's coming in here. Okay, Jolene.
Morning.
Good morning. Actually, this is going to be good for you because you said it's been about 5 years since you've had this crap.
Yeah.
Okay, it's going to be good for you because it'll serve as a review. Unfortunately for Jordan and Jessica, this is stuff that they just had last semester. Do you remember single replacement reactions? Do you know what I'm talking about?
I'm not the only one.
Jessica, Jordan, do you remember them?
We had bad professors the first time.
Yeah, right. That's what you're going to be, that's what you're going to be saying in your next chemistry course.
It's been like 3 years since I've taken chemistry.
Okay.
One,
Who just talked?
me,
Who's-
Jessica.
Jessica, I gotta ask you a question.
Yeah.
Have you ever dumped a guy,
Oh, yeah.
left him for roadkill?
Hmm.
He's down, he's on the curb, he's crying his poor eyes out, and you dumped him for another guy, right? Right?
Yeah, I did. Actually.
And the whole thing is, there is no feeling of guilt there.
No.
All right, let me give you an example. Do you remember the Flintstones? You
Yeah.
know, Barney, Betty,
Fred.
Fred, Wilma. You remember those guys?
Yeah, vaguely.
Okay, let's think. Fred's out with Wilma. He looks across the dining room table. He sees Betty sitting over there. So basically, he looks at the redhead, looks at the brunette, and says, I think I want a brunette tonight. Wilma goes, gone. So Fred goes and hooks up with Betty. So we have a new couple now. We have the Fred-Betty couple, and Wilma is left off in the tears in the ladies' room. Chemicals work the same way. You have a metal, and this metal ion looks over and sees, there's a nice little couple over there. Let's see if I can break them up. And so the metal goes in, nudges his way in, and lo and behold, the anion likes him better. So the anion hooks up with the neutral metal. The neutral metal then gives up his electrons to the cation, and we have an entirely new entirely new couple.
I remember this.
Good. I'm glad I was able to get it that much. So how do we detect if some of these reactions happen? We see them, smell them, hear them, we feel them. Not so much taste, guys. In chemistry, we don't really taste the chemicals. There's something about poisoning that just gets in there and kind of destroys the whole ambiance of that thing. So we're using our senses to detect when we have change. And what are we detecting?
You could see a color change.
What actually is that?
Color change?
Yeah.
What's the name for it?
Yeah, well, no, is it a chemical thing or is it
Yes.
a physical thing?
Chemical reaction?
All right, let's break it
It
down.
could be both.
No, let's break it down, Jolene. What I'm asking is, what are the actual observations? All right, you had a solution that's clear.
Yeah.
Mix the chemicals together, you have a solution that is cloudy.
Yeah.
What are you physically observing? What physical change did you observe? The color, correct?
Yeah.
So the physical properties beforehand are different than the physical properties afterwards.
Yeah.
Does that make sense?
Yeah. You could
So if you
see-
get a change in the physical properties, then you probably have a chemical reaction,
Yeah.
because the physical properties are dependent upon that substance being that substance.
Yeah.
If you change the substance, there's a chance you have changed the physical properties.
The chemical properties.
Well, no, you haven't changed the chemical properties.
You could see it with changing from its form from liquid to solid to sublime to vaporization.
But when you do that, Jolene, have you changed the substance?
Yes.
No, you haven't. If you take water, just water, liquid water, and you boil it up and you see the steam coming up,
No, not with that portion of it. No, but if you fried an egg.
different thing. You're
Chemically
getting a
changed,
chemical reaction there.
And you change the color as well.
You're absolutely right there. When you fry an egg, you get that nice opaque white color, right?
Yep.
But
You can't go back.
that's due to the fact that the albumin has reacted, has chemically reacted because of the heat. And literally speaking, the big long protein molecules have kind of shrunk over on themselves, and they're now basically they have bonded with itself. This big long chain has now kind of crumpled up.
But I agree, sugar water can be changed back physically. So that's a physical change. So I think both.
You think no, you think both. That
With color, I think both. It could be physical or it could be chemical. Because I could give examples of both.
go for it.
Sugar water looks cloudy, but you could,
No, sugar water. If you get sugar in the water,
you saturate it.
and you don't saturate it.
Let's see.
That's
Semantics.
All right. There's no color change.
Semantics.
Okay.
If you saturate it, you'll see the sugar. If you put food dye in a water, red food dye in a water, you can still boil off the water.
And you still have a physical change. Okay.
Semantics. I'm going too far. Just tell me to stop.
I
I haven't had coffee yet. You see how spicy I am without coffee?
don't want to imagine. So, all right, Jolene, if you will grant me this, if you see a physical change or smell a physical change or hear a physical change, then you might have a chemical reaction. Would you agree with that?
I agree.
All right. We're on some sound basis now. So basically what we're doing is we are observing what is changing. And you have to kind of understand the difference between observations and conclusions. The observations are actually what you are seeing that is changing. The conclusion is what you deduce from that observation. For example, you throw an egg in a frying pan. Okay, you see that the heat is making the albumin white. Your observation is, hey, it turned white. Your conclusion is there must have been a chemical reaction to make that occur. Do you see the semantics there between observations and conclusions? And you have to keep them separate. The reason you have to keep them separate is because somebody may use your notes and come to a complete different conclusion. Okay, so what we're going to do in this lab, we're going to look at our reactants. We're going to observe what they smell, feel, or hear. Then we're going to mix them. In a real lab, this is what you would do. You would take the chemicals and mix them. Then you're going to look at the products and see what they smell, feel, or hear. If we detect a change, then the physical properties probably changed, Jolene. If the physical properties changed, then there's a good chance we have a chemical reaction. If nothing changes, no chemical reaction. So that's the whole basis of what we're doing today. Yeah, I went through this. Jessica, you were figured prominently in slide 5. And Barney and Betty. So if I'm looking at a single replacement reaction, what I am looking at is the reactants are going to be a metal and an ionic compound, or they're going to be an ionic compound and a halogen. Okay, we're just going to deal right now with the metal and the ionic compound. All you have to do is look at the reactants, see a neutral metal and a ionic salt. immediately you know that is a single replacement reaction. And what happens if the reaction goes? The metal replaces the cation, so I have a new ionic compound, and that cation will have become neutralized. Again, I'm not saying anything you guys haven't had before, right? This is jogging something in there, right, guys? First rule when we're doing this, the more active element ends up being ionic. What this means is that if you saw some sort of physical change, that means that the reaction proceeded, and that means that the neutral metal displaced the cation. The neutral metal became ionic. If it was more active, the neutral metal will replace the cation. If the reverse happens and I get no physical change, that means the reaction did not proceed and the cation was not replaced. If the cation was not replaced, think logically, it's already ionic. The more active one already is ionic. Why would it change? It's happy. It doesn't have its electrons. It's very, very happy. Now, the second rule we have to realize is if the forward reaction goes, the reverse will not. And that's going to be important in this particular lab because there are going to be some instances where you're going to have to look more carefully because they both aren't going to seem to go. Write this down because I'm probably going to forget it. Temperature is going to become important here. Okay? Temperature is going to be important. If you see a rise in temperature, assume you've got a chemical reaction. All right, let's do some examples. If I throw sodium in with aluminum chloride and I get heat, lots and lots of heat being produced, because that's probably about all you'd see in this reaction. Now, what's happened is the sodium's become Na+, it became more ionic. If it became ionic, then it is more active than Al. On the other hand, if I mixed aluminum metal with table salt, sodium chloride, there is no reaction because aluminum is not strong enough to displace the sodium. The sodium stayed ionic and therefore it's more active than aluminum. Jolene.
Yeah.
You and I are walking through customs, okay? And you're my flunky, okay? Now, I have a kilo of cocaine. I got to get through customs. Am I going to carry it through customs or am I going to shove it off on you?
You're going to shove it off on me.
Okay, so I am now without my cocaine. I walk through customs. You now have my cocaine because I was more powerful. I made you take it.
Yeah.
You, on the other hand, if you're walking in, we're coming off the plane, you already have the cocaine. Are you going to be able to hand that off to me?
It's not reversible. No,
You're a flunky.
it's not reversible.
You're my flunky. You're not strong enough to give that cocaine to me.
Yeah.
So you are going to take that cocaine through. You you weren't powerful enough. You weren't active enough to give the cocaine back to me.
Yeah.
So if your metal is more active than your cation, the reaction will go. If the metal is not more active than your cation, the reaction will not go. And the reverse reaction will not occur. All right, let's look at the second thing. Jenna, I have gold metal with aluminum chloride. I get no reaction. What's more active, gold or aluminum?
Would it be neither because there's no reaction?
Nope.
No.
Oh,
One has to be more reactive than the other. Has to. Which one ended up ionic, Jenna? Leave her alone, Jolene.
the aluminum.
The
I'm not really
it's-
sure.
It started out, didn't it start out at a +3?
Hmm.
I didn't get a reaction, so it ended up as a +3, right?
Oh, yeah. Mhm.
So because it ended up as a +3, it is more active than the gold is.
Okay.
If I did the reaction in reverse, if I put aluminum metal plus gold chloride, would I get a reaction? Guys should be thinking about this.
I'm not sure.
Okay,
I don't know.
Jenna, I mixed
I would say
gold
no.
metal with the aluminum salt. I got no reaction. The
Mhm.
question I have to you is, if I mix aluminum metal with gold chloride, will I get a reaction?
No.
The reverse, or I'm sorry, the forward reaction did not go. If the forward reaction did not go, then the reverse will go.
Oh, okay. Sorry, I'm like,
It's 8 o'clock in the morning and there are cobwebs still there. I understand. But do you understand this concept?
I do get it now. Yeah.
All right. I mix sodium with gold chloride and I get it. I damn near get an explosion. It reacts so violently. Which is more active, sodium or gold? Jordan.
Would it be the sodium?
Because the sodium went from a neutral metal to an ion. It went to be ionic. Now, same question, Jordan. If I mix gold metal in with sodium chloride, do I get a reaction?
Can you repeat that one more time?
If I mix gold metal with sodium chloride, will I get a reaction?
No.
Absolutely not, because the sodium reacted with the silver metal. This is why, girls, you don't need to ever worry about taking your jewelry into the ocean when you swim. Gold is very, very unreactive. And there's a reason for it, and I may get into it later on today. All right. Last one. Let's see who else is out here hiding. Jennifer, how you doing, Jennifer?
I'm good.
Jennifer, I need to talk to you after class, okay? It's nothing major, it's just regarding the final, all right? Okay, Jenna, you have iron with aluminum chloride. You get no reaction. Okay? My iron's a neutral metal. I'm mixing that with the ionic salt of aluminum. I get no reaction. What's more active?
Do you want me to answer it or
Yep.
Jenna? You said Jenna.
No, Jenna's already, I bothered Jenna enough.
Okay, so I would say aluminum would be stronger because there was no reaction.
Exactly. Finish it up then. I think I've gotten everybody. Jessica, do you want to answer one? Might as well, Jessica.
Sure.
All right, I mix iron metal with gold chloride. And I do get a reaction. What
Yeah.
is more active, iron or gold? What ended up ionic?
Iron.
Iron ended up ionic. Which
Yeah.
is more active?
The iron.
All right. Now, I've done all these reactions. I've
We
got-
know we know what's more reactive just by the row they are in the periodic table anyway.
No, you don't.
We know that the halogens are highly reactive because they need an electron. They just
Okay,
need
but
one.
which halide? Oh, Jolene, what's more active, bromine or chlorine?
Chlorine, because it's higher up on the chart.
Okay, you got me. You got me there. It doesn't always work that way.
Well, give me an example.
Iron and aluminum.
I need
Aluminum's
my
high.
chart. I need my chart in front of me because those are the ones we usually use. I need my chart. Where's my chart?
Trust, Jolene, trust me, you can't use the periodic table to do this. Okay?
Iron or aluminum?
That's a bad example.
That's how Maria Bolivian taught it. That's what I do remember.
Okay.
Do you know her?
No, I don't.
She's a colleague of yours.
Sorry, who?
Maria Bolivian?
Don't know her. Sorry. Jolene, use it as a very, very rough indicator, okay? I'll be honest with you. That may very well be true, but I'm not going to vouch for it, okay?
Okay.
Does that make sense, Jolene?
Yeah, maybe I should delete it from my memory bank. I don't know why I
No,
remember
no,
that.
Jolene, it may be perfectly valid, but I'm not going to vouch for it. Okay? Jolene, we agreeing?
Okay, I hear you.
All right, so we have lots of information. All right, we know that sodium is more active than aluminum, and aluminum is more active than gold. What can you say about the relationship between sodium and gold?
Sodium and gold, they're
Sodium is more active than aluminum. Aluminum is more active than gold. What can you say about the relationship between sodium and gold?
reactive.
Strength-wise,
Sodium stronger.
sodium is stronger. Just logically looking through that, I forgot what kind of a logical argument it is, but you know that if you have two statements, you can make a statement about the other two. Now, I also know that iron is less than aluminum, but it's bigger than gold. All right. We've already assigned these kind of a ranking. We know sodium is bigger than aluminum, which is bigger than gold. We also have more information that iron is less than aluminum, but it's greater than gold. Where is that going to fit in my activity series? Iron is less active than aluminum, but more active than gold.
Iron is less active than aluminum, but more active than gold.
I didn't hear you, Jolene.
I'm restating it because I wasn't listening. Iron is more active than aluminum, but
Okay.
less active than gold.
We've already seen from just these two statements that our activity series goes, sodium is more active than aluminum, which is more active than gold. We throw another reaction in here, another couple reactions. And we know that aluminum is more active than iron, and iron is more active than gold. So keep that in mind. Aluminum more active than iron, iron more active than gold. So if I am looking at this, I already know sodium, the activity series from strongest to weakest goes sodium, aluminum, gold. If I know that aluminum is greater than iron and iron is greater than gold, where does iron fit in that activity series?
Would it go after the aluminum and before the gold?
Exactly. Right now, from the previous slide, we know that this is our activity series. If I have these two bits of information in there, then I know that iron is going to go between the aluminum and the gold. Any questions about building an activity series? Let me see where else I am. Okay, I want to do, let's do this first. All right. So you have two metals. Jennifer, you have two metals and you have to determine which one is more active. Design an experiment to tell me which is more active.
Based on the active series that is given.
Better yet, I need another cup of coffee. Can you guys talk amongst yourselves? Do you have that ability?
Only if you could pass one through the monitor and hand it to me.
I am going to go get a cup of coffee. I'm going to give you 5 minutes. What
All
you
right.
guys have to do is you have to design an experiment to tell whether tin or calcium is more active. I'll be right back.
All right. Let's get the periodic table out. And we'll be able to tell things a lot easier. Oh, someone has one. Unmute your phones, girls, so he can hear us talking. So 10 is right. What's the symbol for 10?
I forget honestly.
SN, I'm pretty
Okay.
Which one? FE? No, that's fine.
FN.
The
FN? Okay.
Yeah.
Where's it at? What line? What row?
where the hell is it? Oh, yeah, it's SN. It's
Oh, SN. Yes, that's right. SN. Now what row is that in?
14.
14? That's a line. 14. Got it. Okay. And then the other one is calcium,
Oh,
and that's in row 2. So calcium and 10. I'm thinking
So do you do this based off of the number of electrons?
well, the less, if you're missing one electron, it's very easy to snatch another electron, which would make you highly reactive. That's why we have the halogens, as you mentioned. They're usually cleaning agents like bleach and those things, because they're highly reactive. They grab onto something really quickly and remove it. So that's why you see those things in your detergents and your soaps and things like that. A very small dose, because a pure form of it would erode you, because it's highly reactive. And then you have your last row that's not reactive at all, because it already has all of its electrons in its orbit and doesn't react with anything. So I'm thinking out of the two, calcium is pretty strong, and it's missing a few. 10 is missing 3 electrons. Calcium's missing more, but I think calcium's higher up. I'm talking
Jolene?
shit.
Jolene, 4 or 2?
Yeah, 4 or 2. But I'm thinking
10 has an oxidation state of +2 or +4.
oh, 10 does. So then I would
Yes.
think
That's-
calcium's stronger.
oh,
But the question isn't deciding which one is stronger. The question is,
Trying to
how do-
experiment. So
how do you
calcium plus 10 is reactive.
in what form?
I think you might need to add some heat.
Look what we did to determine whether iron is more active than gold. What did we do?
We did like a modus ponens type situation.
Look at the reaction. What did we add to what to prove that iron is more active than gold?
We added a halogen.
Nope.
I see chloride 3.
Chloride 3 is a spectator ion, does not enter into the picture.
Well, I think we would have to take the
What did we do? What did we physically put together?
Like a chemical reaction.
Yeah, what chemicals did we put together?
So go back to the next slide that you made,
Which next slide? This one?
the one we made up, calcium and you're gonna have to have 10 plus 2.
Go ahead.
So calcium 10 plus 2 would be reactive.
What form's calcium in?
Pure, regular,
Okay.
stable.
All right. You're taking neutral calcium
Neutral is the word I was looking for. Thank you.
and you're adding a salt of tin.
2.
Do you see that? Do you see that, girls?
So was I right?
You were right.
Hallelujah, it's coming back to me. I feel like I'm Celine Dion singing It's All Coming Back.
Please don't.
No, I can't sing.
Oh my
I
God.
can't sing. You don't want to hear it. Y'all will all hang up or not invite me back.
Especially Dion's song.
Oh God, she's great.
Okay. Bottom line, if you want to make an experiment to determine whether two metals are more active, then all you got to do is take the neutral metal and put it into a solution of the salt of the other metal. This would work just as easily as,
The point is we want to have 8 electrons in the orbital when we're done.
you will have 8 orbitals.
Okay.
You have to.
Yeah, that's what I'm asking. Yeah, that's what I remember. That's all I remember.
So guys, in this case, calcium, you mix the calcium neutral metal with the salt of the tin chloride, or you take the tin metal and you mix it with the salt of the calcium chloride. One of these two reactions will proceed. They have to, because one has to be more active than the other. And one will proceed, one won't. You base upon those observations which one is going to be more active.
Can we make a conjecture?
I think the calcium is going to be more active.
Me too.
So if I mix the tin with the calcium chloride, just saying, Jolene, and I get a reaction, what's the cation after the reaction proceeded? Tin is. So because tin is now the cation, it is the more active.
Does 10 break anything down? Can it?
Can tin break something down? Yeah, gold. Gold does
Well,
not
don't they mix
react.
10 and gold together to make like 10 carat stuff?
I actually don't know metallurgically wise what metals they use in alloying gold, but definitely your rings are not pure gold, or else they would flatten
Bend.
out like crazy.
Yeah. Yeah.
I want to go in one thing that I didn't mention, and it's because of Jolene.
Oh no. I'm gonna hit the mute button.
Okay. Halogens, this is definitely true. Fluorine is greater than chlorine. I hate this. This particular slideshow. Fluorine is greater than chlorine, which is greater than bromine, which is greater than iodine. You know this because fluorine is more electronegative. Fluorine's more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine. So if given the choice between fluorine and iodine. Which one is going to have the negative charge?
They all have a negative charge.
Nope.
You
Not,
mean,
not if you put fluorine negative and iodine neutral,
oh, okay, got you.
or iodine.
So
negative
fluorine would
and
be your
fluorine
cat.
neutral.
Fluorine would be your cation, and iodine.
No,
would be,
no, anion. They're making negative charges, Jolene.
You're saying mix these two together and see if there's a reaction.
Mix those two together and see if you get a reaction.
Ooh, I need my battery charger. I'll be right back.
Okay. When we are dealing with the halogens, we are looking at going from the diatomic neutral molecule to the singly charged negative ion. That is what's happening in single replacement involving halogens. We're no longer looking at the metal reacting with the cation. When we're dealing with the halogens, we're looking at the diatomic neutral molecule reacting with the anion of the ionic compound. So instead of Fred and Wilma, and Fred seeing Betty over there, Fred and Wilma go into a bar and Wilma sees Barney.
Yeah.
So it's a different switch here. So when we have the halogens, we're going to have a salt of the halogen, which is going to make the halide ion. And we're going to mix that with the diatomic molecule, the diatomic neutral molecule. Because fluorine is more active than iodine, when I put sodium fluoride with iodine, the fluoride is already negative. I get no reaction. On the other hand, if I put sodium iodide plus
You get a
I
reaction.
do get a reaction.
Yeah.
And in this instance, I got to balance everything.
Yeah.
Are we fairly good with this? Jennifer, you good?
So far, I'm understanding.
Vanessa, you good with this?
Yeah, I'm good.
All right. Now, this leads us into why. Why does this happen? Why are the activity series, why are they made? Why is one more powerful than the other?
Because of the electrons.
Absolutely. So if I've got this reaction, if I have magnesium metal mixing in with copper chloride solution to make magnesium chloride and copper, and this does work. If I split this up into my ionic equation, I get magnesium solid plus copper plus two chloride ions, yielding magnesium plus two chloride ions, and a copper solid. Everybody's seeing how we went from the overall reaction to the ionic. Again, this should be nothing absolutely new to you. Is that true? Are we good? We understand this? Now, when we go from the ionic to the net ionic, look, the chlorides are the same, left and right. The chlorides do nothing. The chloride did nothing more than bring copper to the show. It did nothing more than bring copper to the show and leave with the magnesium. That's all it did. It wasn't involved in the reaction. So what we had in the net reaction here was we had magnesium solid reacting with copper ion to make magnesium ion and copper solid. All of these single replacement reactions can be broken down to something like this. And what it comes down to is something is losing electrons. In this case, the magnesium is losing 2 electrons. The copper gained those 2 electrons. We have a loss of electrons and we have a gain of electrons. That is called a redox reaction. Reduction is a gain of electrons. So when we did this, if we were just looking at the copper half of this reaction, then what was happening was the copper was grabbing 2 electrons to make neutral copper. If we look at the magnesium half, the magnesium was, forgot to finish this out. What the magnesium was doing was it was relinquishing its, giving up its 2 electrons and staying as magnesium ion. So this is really, really what is happening in these reactions. You can remember this through oil rig or Leo goes grr. I don't care, I stole both of them. Oil rig, oxidation is loss of electrons. The rig portion, reduction is gain of electrons. If you like, Leo goes grr. Loss of electrons, oxidation. Grr, gain of electrons, reduction. Either way, it's a nice, easy way to get to memorize this. Now we come to that part of the show in which Mr. Popovich would like to slap silly the idiot that ever started to call these things these things. We get into semantics, and you got to learn the semantics because unfortunately they haven't uniformly said, oh, this is an oxidation, this is a reduction. They've wanted to make things, they want chemists trying to use English, which is never a good idea. Have you ever read chemistry books? Boring as snot. Chemists cannot write English at all, except for this one who has an English degree. But present company accepted. We have to deal with semantics. An oxidizer or oxidizing agent is something that causes another substance to be oxidized. That substance is actually undergoing reduction. A reducer or reducing agent is something that causes another substance to be reduced. That substance is actually undergoing oxidation. So the substance undergoing oxidation is a reducer or a reducing agent. The substance actually undergoing reduction is an oxidizer or an oxidizing agent, and you will see these terms liberally distributed within the same sentence. Somebody will call something undergoing oxidation acting as a reducing agent. You just have to learn to deal with it. Another rule, this is an absolute rule. You can't have an oxidation without a reduction. You cannot have a reduction reaction without an oxidation. You can't have a buildup or a depletion of electrons in the universe. Whatever electrons are created, they have to be absorbed somewhere. So what happens is if I pair, and I have no idea why this happened. If I pair my two half reactions, my copper absorbed the same amount of electrons that my magnesium gave up. I'm absorbing and producing electrons. I have an electric circuit. Basically, you have just created a battery. This is what batteries are. Every one of these half reactions is compared to a standard, and it's called a SHE, a standard hydrogen electrode. And that is where two H pluses, an acid, gains two electrons to create hydrogen gas. When I hook a standard hydrogen electrode up with a magnesium half cell, I get production of 2.37 volts. If I have 1 molar acid and 1 molar magnesium salt. On the other hand, if I hook that standard electrode with copper, I only generate 0.34 volts. And notice the plus or negative sign. That's going to become important in a second. So all of the reductions are related back to a standard hydrogen cell. And basically, we rate how much voltage is produced when it's hooked to that half cell of hydrogen. Some rules when doing this. A, you can't have an oxidation without a reduction. If you flip a reaction, in other words, if you turn a reduction into an oxidation, you flip the sign of the voltage. The third rule, you want to have a positive voltage to have a spontaneous reaction. In other words, if the reaction goes, the voltage will be positive. And what happens is you have, and I'll try and go to the slideshow to make this a little bigger. You have a table that's formed. You get a table that's formed, and you have, if you notice, all of the reactions are adding electrons. Each one in this table are adding electrons to it. Therefore, it's called a reduction potential table. The standard reduction potential tables. The other thing you have to understand, it's a standard potential, which means that the molarity of the aqueous solutions is going to be 1 molar. You're going to need that when we go on to non-standard cells in lecture. But basically, we are relating every one of these reductions to one another. We're relating every one of these reductions to one another by the standard electrode. Do I have you all here right now? We good? Is what I'm saying making sense, guys? Now, we're going to use this table to determine which element is more active. Because remember, we have to have an oxidation reaction and we have to have a reduction. If I put nickel and iron together, right now in the form they're in, they are both sucking up electrons. That can't be. One of them has to give up electrons while the other sucks them up. So one of these reactions has to be flipped from the oxidation to the reduction reaction. If you have your TRO in the 5th edition, it's on page 909. There's a very good chart there. You are going to need that. You are going to need that for the upcoming, for not the lab that's due from this lecture, but for the one that was due on Tuesday. You can also just Google a standard reduction potential table, and it will pop up for you. But that is your responsibility. All right, remember, all of the reactions in the table are reductions. So one has to be flipped. If I am looking, and I have to get out of this end show thing because I noticed a mistake. Okay, if I am looking at a cell between nickel and copper, if I look up the reduction potentials for both nickel and copper in that table, I find that nickel is a minus 28 and copper is a plus 34. One of those two reactions has to be flipped around. And when I flip it and add the two potentials together, I have to come up with a positive voltage. So which reaction am I going to flip to get an overall positive voltage?
Would you flip the nickel and make it positive?
Absolutely. I'm going to flip the nickel. I have to flip one of them. I can't just add these two together because they're both reduction reactions. One of the reactions has to be an oxidation. So if I flip the nickel, I end up with nickel going to nickel plus 2 electrons. That standard voltage is a 0.28. I add that to 0.34. My overall voltage for my standard cell is 0.62 volts. Now looky. If I add my two half reactions, bear with me a second. I realize you can't see this. I'll try and make it bigger in a second. Can you see that now?
Yes.
Now, what I have done is I've just basically added these two half reactions. So that now when I've added it, I got nickel metal reacting with the copper ion to make nickel ion plus copper. Can you tell me what is more active, nickel or copper?
Nickel.
Nickel is more active because it ended up ionic. If I flip both of these reactions and have copper metal plus nickel ion, possibly making copper ion and nickel metal,
Would be in the negative.
this would be negative.
Would be wrong.
Negative voltages are not spontaneous. They do not happen. It's
Yeah.
only positive ones. So basically, you have the ability to look at a reduction potential table and Determine your own activity series just from that.
What about those 4 electrons we have floating around?
They got absorbed.
They got absorbed into the nickel?
The nickel produced them. Jolene, nickel produced them. They were absorbed by the copper. That's where they went.
Oh, okay, so we're doing the 2, adding them together. Gotcha.
Okay, again, that is a standard potential, which means they're run at 25 Celsius with 1 molar solutions. This is the way the reaction will proceed. In other words, nickel is more active than copper. If I put the nickel ion with copper metal, I'm not going to get a reaction. I have a single replacement cell with aluminum and zinc. I need a positive overall addition of these two. And also you have to realize one of the reactions needs to be flipped.
Yeah.
Which one is going to be flipped so that when I add the 2 of them together, I'm going to get a positive result?
The first one.
I'm going to flip the aluminum. When I flip the aluminum, the voltage went from a negative 1.66 to a positive. I add that with the negative 0.76 voltage of the zinc. I get a positive 9.0.
So I have a really stupid question because I keep seeing this over and over again in your slides and I never heard it this way. When you have the zinc 2+, you call that a zinc salt?
Yeah.
So anything
What-
that has,
Can I have a positive ion with no corresponding negative ion, Jolene?
that's what I'm asking. I just never heard that
No.
before.
You cannot have, it's not possible. You can't have positive ions out there without a counterbalancing negative ion.
So you call it a salt.
And basically, whatever the anion is, if it's nitrate, then when you do this, when you put the aluminum in the zinc nitrate, the anion that was the forming the salt with zinc now is the anion for forming the salt of aluminum.
Okay.
It's just spectating. It doesn't have anything to do with the overall reaction.
No, I understand. I just never heard it called that way. It's interesting. Something new I learned. I like it.
So basically, this means if I put aluminum metal into a zinc salt solution, I will get a reaction. If I do the reverse, if I put zinc metal in an aluminum salt solution, I will get no reaction. Okay.
Yeah.
Yeah, I'm sorry. What happened is I flipped
Negative, yeah.
I'm sorry, I flipped that. I did this slideshow very quickly. I'm sorry. If I flip the reaction, I get a negative potential here. If I get a negative potential, that means the reaction does not go. I have to have a positive number there. Now, am I creating electrons here? If I just have this reaction with this reaction, am I not producing, for every mole, am I not producing 1 mole's worth of electrons? Because aluminum is producing 3, but zinc is only able to suck up 2. Isn't that true? Jessica, does that make sense to you?
I'm sorry. Can you repeat?
My aluminum produces 3 moles of electrons for every mole of metal that's consumed.
Okay.
But zinc is only able to absorb 2 of those moles for every mole of zinc ions it has. So if I let this go just as it is, can you see that I'm overall producing electrons?
Yeah.
I can't let that happen. I have to balance the electrons that are produced with the electrons that are absorbed. I can't have an overabundance of electrons. What gets produced has to be absorbed. So I have to multiply the top equation by some number and multiply the bottom equation by some number so that the electrons are going to be equal. What
Okay.
number am I going to multiply the top equation by?
2,
2. And the bottom one?
3.
I now have 2 aluminums yielding 2 aluminum ions plus 6 electrons. I have 3 zinc ions absorbing 6 electrons to make 3 zinc metals. And believe it or not, you have just balanced that equation. One of the first things you're going to do when you get into electrochemistry is you're going to learn how to balance complex redox equations. And we are going to do this specifically. Even if I put in the anions, they are going to be balanced as well. Because if I put the 3 in front of the zinc ion, zinc has to have 2 nitrates to balance it. So that means I have 3 times 2 or 6 nitrates on the left. Aluminum has to have 3 nitrates. So when I pull down the aluminum coefficient, I have 2 times 3, 6 nitrates. It works out. So the spectator ions also get balanced in this particular situation. Now, when we're dealing with the cell, have you all heard the terms anode and cathode?
Mhm.
Guys, yeah?
Yeah.
One is a positive electrode, the other is a negative electrode. The easy way to tell which reaction is occurring at which electrode, vowels or consonants. Oxidation occurs at the anode, O and A are vowels. The reduction occurs at the cathode. R and C are both consonants. So remember, at the oxidation site, we are producing electrons. So that's the one that's negative. At the cathode site, we are attracting those electrons. We're attracting them because the cathode has a positive sign.
That makes sense. When I'm doing electrophoresis,
Go for it. Talk about it.
the anode side like produces the electron field, and then the electrons go towards the cathode. So
What are you doing? Are you doing biochem, Jessica?
I do biotech.
Okay, so you're actually, are you doing DNA or?
Yeah, we were doing DNA and biotech 1.
Very, very fascinating, because actually what they do in DNA analysis is they take a strand of DNA and there are certain chemicals that break the DNA at certain points. But everybody's little fragment is just a little bit different from everybody else's. So they just have a certain number of loci that they attack with these chemicals, and it breaks the molecule. And because the broken chains are a little bit different from somebody else's, what you get is you get something that looks like a barcode reader.
Mm-hmm.
And that's how you analyze the DNA sample. Sidelight. All right, I have to get into this other reaction. I have to get into this other equation because he brought it up. When you are dealing with non-standard conditions, you have to involve something called the Nernst equation. You have to realize, Jordan, didn't you just at the start of class, didn't you spend all that time putting it into a ponytail? Jordan. She's not answering me. Jordan, didn't you take about 5 minutes putting your hair into a ponytail at the beginning of class? She's not
I'm sorry.
reacting.
I don't know if you were talking to me, but my whole screen just like froze.
I'm sorry. Jordan, what I said was, didn't you just spend about 5 minutes at the beginning of the class putting your hair into a ponytail?
Yeah, I can never decide what I want to do with it.
All right, fair enough. Okay, I have two reactions. I have gold and magnesium. Okay, and they are a reduction and an oxidation. I get a positive result. They are in the right, they're in the right order. Okay. First thing I have to do is balance the electrons. What am I multiplying the top by, and what am I multiplying the bottom reaction by? Go for it, Jordan.
The top by 2 and the bottom by 3.
I know it sounds silly, but we're going to have to do that. So notice that I'm generating 6 electrons. The magnesium is producing 6. The gold is absorbing them. And this is my overall reaction. When I add these two half reactions together, the gold comes down as the gold ion. The magnesium comes down as 3 magnesium. I've generated 3 magnesium ions and 2 gold metals. What we've gathered so far from adding the potentials together, we know what the standard cell potential is. We know that gold is the cathode and magnesium is the anode. We know that because the reduction is occurring, gain of electrons, reduction's occurring at the cathode, oxidation is occurring at the anode. We know that 6 electrons were exchanged. And if I'm going to look at this overall reaction, remember our equilibrium constant expressions. If I want to get the Q for this reaction, remember, we don't use solids when we're doing an equilibrium expression. Solids do not get used. So if I'm looking at this reaction, I've got my concentration, my Q is going to be my concentration of my Mg ion quantity cubed divided by my concentration of gold ion quantity squared. Is everybody seeing that? Seeing how I got the Q? To explain it again, I took my 2 half reactions, added them up, and I created my overall reaction. When I'm dealing with an equilibrium expression, I don't use solids. So I don't deal with the solid magnesium. I don't deal with the solid gold. I then put the concentrations raised to the power of their coefficient of the products over the concentration of the reactants raised to their coefficient power. So if I'm looking at this Q expression, it is Q is equal to my concentration of my magnesium ion cubed divided by my concentration of gold ion squared. Have I lost anybody so far? Okay. My Nernst equation. My E of cell is going to be my standard cell potential minus this 0.0592 is a constant that we're going to develop when we get into lecture. I'll show you how that evolves. But it's 0.0592 divided by N, the number of electrons that are exchanged, times the log of Q. And I may have screwed up here. See if I screwed up in a second. Okay. And I'm without a pen. Sorry, guys. Okay, sorry. Okay. So this is my overall Nernst equation. My E cell is going to be my E standard cell minus 0.0592. And I've screwed up already. Okay, sorry. My E cell is now going to be my E standard cell minus 0.0592 divided by the number of electrons times the log of Q. I plug the numbers in. I get 4.20 volts minus 0.0592 divided by 6 times the log of 2.75 cubed divided by 0.015 squared. I do the math of this part out. I get 0.04 subtracted from 4.20. My E cell is now going to be 4.16 volts. Any questions, ladies and gentlemen, or ladies? No gentlemen here. Present company included. Are you understanding how the Nernst equation works? You got to figure out what your equilibrium expression is. Then plug your non-equilibrium concentrations into that equilibrium expression. And you're going to plug that value into the Nernst equation. And whatever it comes up with is going to be your E cell. Any questions, ladies? The simulation is going to be not fun. I hate to say this. Where am I at? I'm going to stop share and get into the all right. Courses. Okay. Yeah. You got a whole bunch of reactions to run for this particular experiment. Don't shoot me. I'm only the one. I'm only the one delivering the message. Got some introduction there. Your report sheet. Yes, you have to do all of them. You're mixing silver nitrate. Silver nitrate's a solution. You're making 4 different flasks with the silver nitrate in it. To each one, you're adding copper to the first one, zinc to the second, lead to the third, magnesium to the fourth. If there is no reaction, then there is no net ionic equation. Just put no reaction there. Realize that you are putting the metals into silver salt, into the silver ion. Later on, say for example, we have copper. There's going to be another instance where we're going to have the copper salt. Lo and behold, we have the silver metal. Just understand, you have the metal in one instance, ion in the other. That's the first reaction in set B. Understand that you've got the silver ion with copper metal. One of those 2 reactions has to go. They're kind of a check on the system. If you get one to go, or if you get both to go, you've done something wrong. If you get neither to go, you've done something wrong. And there are a series of 1, 2, 3, 4. So you're going to be doing 16 reactions. 16 reactions. Maybe more than that.
Okay. Is this all due on July 4th?
No. No, I've kicked this out to be July 11th.
Thank you.
All right. But also due on July 11th is the next lab as well. Okay. The next lab is not nearly this harried.
So but the Tuesday's lab is due Sunday. This one's the 11th, the next one's the 11th.
Correct. I
Okay,
have, Jolene, I have to do it that way because you're taking your final on the 13th.
really, we're done?
You're done.
Jeez, I need to open up a calendar.
The final is occurring on the 13th. Unfortunately for you, it is a multiple choice test. I say that's unfortunate because multiple choice test means no partial credit. And I've looked at it. It is hard. I'm sorry. I have looked at it. It does
Can we
look
have
hard.
can we have like a review with you?
That is what's going to happen a week from today.
Yay. A really good review? Like a really, really, I mean, I'm just like, you know, right at the little, like the below average.
The way
mark.
I do,
need a lot of
Jolene,
help.
Jolene, the way I do reviews is I make myself available. You have to provide the fuel for the review. You have
I'll
to ask
exercise
questions.
that. I'll exercise that right.
I will be here. I will be here from, I have to start my lecture at 10:15. I will be here from 8 until 10. Fair enough?
Extremely fair. Thank you.
Okay. Then, after you do all those, he makes you go through the, you're putting, when it says iodine water, that means I2 in water mixed with the bromine ion. So this is the I2. The sodium bromide would be the Br minus. The NaCl would be the Cl minus that's added to I2. You're to make observations. This case, you're doing bromine water. You're adding I minus to bromine, Br2. You're adding Cl minus to Br2. This one, you're adding Cl2 with I minus and Cl2 with Br minus. From all of that information, you've got 5 ions here. When he's got SOAWRA, he's got strength of the oxidizing agent. All right, oxidizing agent means you're producing electrons. So this means that the metal is going to react with the salt. Give me an activation series. Just put most active to least active. Is that fair enough, guys? Most active to least active. I'll understand what you're doing, and you're going to do the same thing here. Again, very, very long lab. I know that. Okay. What he wants here, can potassium metal act as an oxidizing agent? In other words, can it be reduced? In order to be reduced, it has to gain electrons. Can potassium gain electrons to be K minus? Come on, answer the question. Can potassium gain electrons to be K minus?
If it gains electrons,
It's a
it will
metal.
be.
It's a metal. Can a metal gain electrons to become an anion?
Sure.
No.
No, that's what I said. What are you talking about? I said no.
A metal cannot gain electrons to become an anion. If potassium were going to be reduced, it would have to gain electrons, which would make it an anion. So can it be an oxidizing agent? No. Don't put anything in the in this space if the answer to this is no? Can it be a reducing agent? In other words, can potassium be oxidized? Can potassium lose electrons to become K plus?
Yeah.
Yes. Oxidation half reaction. K yielding K plus plus 1 electron. Can Fe plus 2 gain electrons to become Fe neutral?
Yep.
Then yes, it can act as an oxidizing agent. The reduction half reaction would be Fe2 plus yielding Fe0 plus, I'm sorry, Fe2 plus 2 electrons yielding Fe0. Can it be a reducing agent? Have you ever heard of Fe3 plus? Has anybody ever heard of rust? Fe2O3.
Oh, no.
So isn't the charge on the Fe a plus 3? Isn't it a plus 3?
Mhm.
So isn't it possible for Fe2 to go to Fe plus 3?
Yeah.
So yes, it's also possible for Fe2 plus to be an oxidizing agent and a reducing agent. The Fe2 plus can lose 1 electron to be Fe3 plus. And there's more. Here, you're going to have to look at these particular things. A, B, and C can all act as oxidizing agents. Think of this as a puzzle. In solution, A is green, B is yellow, and C is red. Notice no charges on there. If A goes to A minus, it's colorless. If B goes to B minus, it's colorless. And if C goes to C minus, it's colorless. So you got to figure out what's being produced, what ion is being produced. If C is mixed with B ions, I get a color change from red to yellow. What species am I producing? A, B, or C?
B.
If I'm producing B, I should get a yellow color, correct?
Mhm.
So this means that my B minus reacted to make B. If my B minus reacted to make B, then what ended up ionic? Did the C end up ionic or did the B minus end up ionic? Did I get a reaction? Did I get a reaction, guys?
Yeah, you got a reaction.
Yeah.
If I got a reaction, did my C turn to C minus? Remember, I'm
Your
mixing.
C turned to C minus and your B turned to B neutral.
Okay. So what got oxidized? What got reduced?
Reduced would be C and oxidized would be B.
Correct. Because the C went to C minus.
Can we use the other words, anode and cathode? Because I'm still confused with those words.
And you just, anode and cathode, the oxidation. Okay.
Is the oxidized, the reduced is cathode and the oxidized is anode, is that right?
Reduced is cathode, oxidized is anode.
I had it backwards.
Just remember, vowel, vowel, consonant, consonant, Jolene.
Okay, I'll try.
All right, when it's saying oxidized, that really does mean oxidized. It is the thing that is losing electrons.
Uh-huh.
The B minus went to B, the B minus lost electrons.
Yeah.
That would be B minus. The C gained electrons, so the C was reduced.
Yeah.
Do the same thing for this next one.
This is the never-ending lab. Jesus.
I haven't gotten to the second one yet.
Stop it. I'm gonna go find Dr. Lou. I'm gonna tie him up in the janitor closet. No, I'm kidding. This is
Doesn't-
crazy.
Okay,
Crazy lab.
okay.
If we were in a classroom setting, would we be able to complete this lab in an hour?
The labs are 2.5 hours long.
Oh, it's been so
Jolene.
long, I forgot.
It's one of those side things that goes by the wayside. Okay. Voltaic cell. Do I need to go through the simulation with you guys? It's the same simulator you've been using in the past where you grab it from the stock room, put it to the experimental table, and you just add a little bit of each one. Do I need to go through that with you?
I don't think so.
No.
Okay, report sheet for this one. Okay. You are going to be given a survey. Okay. And the survey, you're going to be given a table with the standard voltages and the non-standard voltages. SC stands for standard voltage, the standard cell, or the standard results. NC stands for non-standard cell. So you will be given these voltages. And you need to determine what the anode and cathode is from that. Okay. You're going to have the standard cell, basically calculated voltage. This is that reduction table I told you about. Okay. This is the reduction potential table I told you about. All you got to do is flip one of the reactions and add them so that they end up being positive. Okay. Measured voltage you're going to get in the survey. Difference, take the 2 and subtract them. Percent voltage, you are going to do this minus this over the calculated voltage. You're going to need to do the Nernst equation for NC 1, 2, 3, and 4 to determine what the calculated voltage is. You're going to be given a measured voltage, give the percent difference. And you have a more reasonable, you see, this one's not bad, Jolene. This one is not bad.
Never know.
All right. Now, I am not encouraging you to do this. But remember, hint, hint, nudge, nudge. One of your laboratories gets dropped. Part of becoming a student is realizing what work you have to do and what work you don't have to do. If your lowest grade is something like an 80%, then understand you are doing that single replacement, that big long single replacement lab for a possible another 20 points. You have to make the decision on whether you need those 20 points. Are you understanding what I'm saying? Your lowest lab gets dropped. So if your lowest lab is something like an 80, then what's going to happen is from your total points right now, I'm going to subtract out those 80 points and replace it with whatever score you get on that single replacement lab. Nudge, nudge, wink, wink. So you got to understand, you got to ask yourself, is it worth my time and effort to go through and do that laboratory? Sometimes you got to pick and choose what you expend your time on. That's all I got, guys.
Thank you.
Thank you.
Does anybody need to go through the simulation? By the way, I will be, if you want to look at these laboratories sometime over the weekend, I will be back here absolutely next Tuesday. I will be here next Tuesday. I will go over just what we went through in the second half today. And I will be here next Thursday for a review.
Wow, that's the end. Okay, so just to be clear, this whole thing today is due on the 11th.
Both laboratories.
Perfect.
That's all I got for you.
Thank you.
Thank you.
Okay, I need to talk to Jennifer for a second, and I always stay until you guys get out of here. So unless you have questions,
See ya.
Jennifer, you're the only one in here now. It's, I mean, basically it has to do with when are you taking the final? You are leaving on the, I understand you're leaving on the 13th. Is that correct?
No, I'm actually leaving the 14th. They changed the flight dates to be later on the 14th.
Okay, so then we have no conflict. Right?
We have no conflict. Well,
You can-
the flight is originally the 13th going on to the 14th. So it's basically almost the whole day of 13th on to the 14th. Like we have 2 stops and it's big hours of waiting till the next flight.
Okay, so I'm trying to, that's what I just asked Jennifer, and you just said it got changed to the 14th.
Basically, I would come back the 14th.
The information I need to know. Wait, you are going to be here on the 14th is what you're saying.
But the flight starts early the 13th. So basically the 13th and the 14th, I won't be
So
available.
bottom line, if I was going to be a real nice person, all right. What I have to have from you, Jennifer, I will do this for you. And this is as nice as I can be. Okay? I will let you take the test on, let's see, the 13th is a Thursday, right?
No, it's a Tuesday.
It's a Tuesday?
The 13th, yeah.
Why is that not popping up for me? Okay. Yes, thank you. All right. I have to get grades in 48 hours after my final, okay? Jennifer,
Okay.
I will be all ready to go. This is a multiple choice test that you're going to have to take. I'll give you, I know you're going to be jet lagged as hell, but there's nothing I can do about that. Okay?
Okay.
As a matter of fact, where are you going? Which way? East or west?
We're going to Dominican Republic, so it's more on the Caribbean side.
Okay, so you're not going to be jet lagged. You're going to be more or less on the same time zone.
I would believe so.
All right. So what you're going to have until the 15th at noon to take the final for this class.
Okay, so till 12 p.m. on the 15th.
Yes.
Okay.
Is that fair enough, Jennifer?
Okay.
Okay. So you're leaving like sometime like right now, right?
Roughly around this time, yeah, on the 13th.
No, all right. I need to understand this. Your vacation is before the 13th, correct?
The vacation starts the 5th,
Starts the 5th to the 13th. Okay.
13th ongoing, yeah.
All right, Jennifer, for the lecture, you're going to have to really look at the videos. You're going to have to look at my lectures online. I will upload those Zooms, but you're going to really have to also look at the videos because we are getting into something called entropy today. Okay? That's today. We're going to complete it probably end of Tuesday, and we're probably starting on electrochemistry on Thursday. Electrochemistry, we're going to be spending a great deal of time on redox balancing reactions the first day. So that's, and what I'm thinking is you're going to be missing, you're missing 3 classes, aren't you, Jennifer?
I could do the 8th, but the Tuesdays are on the flight days. So the 6th, I would have to watch your lectures. I wouldn't be able to attend.
Okay.
Because the flight is like early. And then the 13th, I am hoping that I can actually like squeeze in your class because right after your class, I would have to be ready and like going to the airport.
Okay. Bottom line, as I recall, I've got the 1st and the 6th are going to be entropy. That chapter. 8th, this is what it has to be. The 8th and the half of 13, 8 and half of 13 are going to be spent on electrochemistry. Half of 13 and 15 are going to be on nuclear chemistry.
Okay.
Test on the 20th, final on the 22nd. Fair enough?
Yeah, I think I'll be able to do the 8th, maybe the 13th, and then I'll be back by the 15th and 20th.
These are the resources you have, okay? Jennifer?
Okay.
Good enough?
All right. And
So you will be done the 15th. 15th, you'll have your lab final, so that will be taken care of. Your other 2 tests are the 20th and 22nd.
And I do have a question for the final for the lab. Is the review very close to what questions are going to be?
I told you how I'm going to review it.
Okay.
I'm basically going to go through the labs. I'm going to highlight the major equations that were talked about. But you are going to be providing the fuel for that review.
Is it going to be open book just like lecture, or we can't have notes?
I don't see how it can be.
Okay.
I really don't see how it can be, Jennifer. I'm sorry.
No, that's fine. And then
I may change my mind on that. I may let you have a 8.5 by 11 sheet of notes. I probably will let you have at least that, okay?
okay. And so what you were referring to about seeing what lab you could do. So let's say I do have like a really good grade. I could only do this one.
That's one
not
second.
really long one.
Let's. All right. I do have to get out of here soon, Jennifer.
Yeah.
Oh, sorry, we're going this way. Ah, crap, I'm in the wrong thing. I'm going to do this real quick, Jennifer, all right? Grades. Okay, we're looking at these guys, okay, the hundreds. Okay. And I'm going to need to take this over, and you're right here. Okay. All right. I'm looking, Jennifer. I'm seeing 95, 94, 100, 97, 97.33, 87.5. Okay. I've graded the solubility product. I haven't put it in here yet. Redox is that big long one, and Voltaic cell. Okay. So hold on a second, please, Jennifer. Okay, 26L. Have I graded that yet? Crap. Did you have a lab? Is the solubility product? That's what we did on. Oh, this is what we did on Tuesday, Jennifer. Jennifer, you with me?
Yeah, that's the one due.
This is the one that's due on Sunday.
before- Yeah.
Okay. This is due on Sunday. I mean, look at your labs, Jennifer. Your lowest lab, the one you're dropping right now, is an 87.5. Okay.
Okay.
Look, what I promised to do for you, okay, is I promise to grade that I'll grade it out of sequence, and I will put it in there. Email me though. Jennifer, email me on Sunday saying that I promised to grade the solubility product lab on Sunday. If you get it to me quick, I can grade it that much quicker. As soon as you do it, as soon as you do that solubility product lab, send it to me. I will grade it. And then you will see whether or not you have to do this redox lab.
So I
And
did turn it in. I
you
already
did turn it in?
I wasn't able to, you didn't post the video, so I just went ahead and I tried looking at like Lou's video and as much as possible what I could complete.
What video did I need to print out?
Usually you always have a video for the labs,
Of the
like
sol
Dr. Lou. Yeah, so I just went off of what he did and try to see the best that I could fill it out. And I
didn't
turned
put
it
the
in.
Zoom in there?
I looked yesterday and I didn't see that you posted the one on the 29th.
Nope. Sorry.
It's okay.
Yeah. It will be posted. As a matter of fact, I probably could post it right now, but it's not going to do you. You've already turned it in?
I turned it in, yeah.
Okay. There's nothing I can do about that now. It's probably going to be fine, Jennifer. I'll grade it today and you'll have the results for it. Okay.
Okay.
But if it's somewhere around an 80% or more, that's a whole lot of work to be doing a minimal amount of get back. Do you understand what I'm saying, Jennifer?
Yeah. I'm also taking the late course that started, which is like biology, and they're requiring so much. So if I don't have to do the redox and I can only do the other one, I would do that.
Let me grade it. Let me grade it. It'll be graded today. And once that gets graded, you can have a fairer idea. But
Okay.
even if it's down to 60%, Jennifer, that's still a lot of work. That's still a lot of work for those 40 points.
Yeah.
I look at that, I look at that thing and I look at it, I thought it was ridiculous. The amount of work required for that lab.
It's 8 pages. I was like,
Mm-hmm. Yes, I agree. I know. I'm sorry, Jennifer, I got to get off now because I got to get back onto the Zoom for the lecture, okay?
for the next one, okay. Thank you.
All right,
See you later. Bye.
see you later. Damn. Top share, end.